Hi and welcome to this video on the definite integral. Here what we do is we're integrating between limits and applying this to areas under graphs. We integrate f of x with respect to x for two values a and b, and then what we do is we substitute into the equation and subtract. So we're going to have two values a and b, that's most important, and then we're going to subtract. So let's have a quick look at this. So if we have the integral of 3x squared dx, then when we integrate we get 3x cubed over 3 plus c. Now because we're going to have two equations which we subtract using a and b, the c's disappear, so essentially we get a c in one and a c in the other, and that's equals 0. So when we do definite integration or the definite integral, we don't use plus c. So let's have a look here. So we're going to write a definite integral with the limits between 1 to 3. So we integrate limits 1 to 3. However, when we calculate it, we first plug in 3 which is the upper limit, and then we subtract minus after we plug in 1, which is the lower limit. So this would then become integral of between 1 to 3, 3x squared dx. This equals 3x cubed over 3, which is x cubed, because this 3 cancels out this 3, and the limits are from 1 to 3. So first of all we plug in 3 and we get 3 cubed, and then we subtract after we plug in 1, which is 1 cubed. We get 27 minus 1, and that equals 26. Also the definite integral between the limits minus 2 to 2, x squared minus x dx. And this is when we integrate, x squared becomes x to the power 3 over 3 minus x then becomes increase the power by 1 and divide by that power becomes 2, between the limits minus 2 to 2. So on this side we're going to put the 2 into here, so this would become 2 cubed, which is 8 over 3, minus x squared, which is 4 over 2, and then we're going to subtract after we put the minus 2 in, so that would become minus 8 over 3 minus 4 over 2. When we do this, then this becomes, taking a common denominator, we get 16 over 6 minus 12 over 6 minus 16 over 6 minus 12 over 6. This is 4 over 6 minus 28 over 6, which is 32 over 6, or 16 over 3. And that is our answer. So let's have another example. So definite integral between the limits 1 to 3 x minus 1 over x squared dx. So this is when we integrate x squared over 2 plus 1 over x between the limits 1 to 3. Now 1 over x squared is nothing but minus 1 over x. That's why this minus becomes a plus. If we have a little thought bubble, if we didn't understand where that came from, so we have the integral of 1 over x squared equals integral of x to the minus 2 equals x to the minus 1 over minus 1, and this is minus 1 over x. So when we substitute this back into here, this is minus 1 over x, so this minus becomes a plus, and we're left with that. Now let's put our lower limits and upper limits in. So this becomes 9 over 2 plus 1/3 minus a half plus 1. So this is 29 over 6 minus 9 over 6, which is 20 over 6, and the answer is that 3 1/3. Area between curves is often a use of the definite integral. So if we have a curve f of x and a curve g of x, and we want to find the area between the curves from A to B. So that's the area we're interested in, is here, and we can write that the area between f of x and g of x on interval a to b is given by definite integral a to b f of x minus g of x dx. When we're doing this, it's very important, so we need to know which is the upper function. And how we do this is we draw a strip between A and B of width delta x. Yeah, I'm exaggerating it a little bit here. So this would be delta x. And then we substitute the x into the function and see which gives us the higher value, and obviously the one with the higher value is the upper function. For the area under a curve, let's consider just a simple area first. So we'd have x and y axes, and we have a parabola, so symmetrical about this. This is y equals minus x squared plus 3, and we want to work out the area here. Well, that's area, and that would be between this f of x and the g of x in this case would be here, which would be y equals 0. Now the first thing we want to do, or we should do, and if we make that habit, is to find out which is the upper function. So if we choose an arbitrary value, say 1, at x equals 1, this would be y equals, for the this function f of x would equal 1 squared, which would be minus 1 plus 3, which would be 2, and for this y equals 0, y equals 0. So this, from our calculation here, is the upper function. So say we can't draw it, we would have to calculate it that way. Now we need to know which are our a values and b values. So we have minus x squared plus 3 and set that to 0. So minus x squared equals 3. So a equals minus square root of 3 and b equals square root of 3. So our a is minus square root of 3 and our b is square root of 3. Now we can do our integral, so it will be the integral, or definite integral, between minus square root of 3 and square root of 3 of minus x squared plus 3 minus 0. We can ignore this 0 comes from y equals 0 because we're going to subtract that, so we can ignore that, so it just becomes minus x squared integral of square root of 3 minus square root of 3 minus x squared plus 3 dx. And when we do this, this equals minus x to the power 3 over 3 plus 3x square root of 3 minus square root of 3. Now we substitute these upper and lower limits into our equation and subtract, and what we get is so this would be minus square root of 3 cubed over 3 plus 3 times square root of 3 minus, and don't forget now we've got a minus here, so this will be minus square root of 3 cubed over 3 plus 3 times minus square root of 3. So when we work this out, we get the answer to be 4 square root of 3. We could have done it another way. We know this is symmetrical about the y-axis, so all we needed to do was just work out this part and then double it. When we work out this, this becomes 2 square root of 3, and then double, we multiply by 2, and that would have given us the same answer. We had a look at area before, and curve and the x-axis, and what we said, it was a definite integral between a and b of y dx. Now what happens if we have an area between the curve and the y-axis? So let's draw a little diagram. So this is the curve y equals 2x squared, and we're interested in this. It's supposed to be straight lines. This area here, which we're going to call A, and between the limits 1 to 4. So this area would then be the definite integral between 1 to 4 of x dy equals the integral of 1 to 4 square root of y over 2. So we can take the 1 over square root of 2 to the outside, which is 1 over square root of 2, and then the square root of y, then it's simply y to the power a half. So we did this as a little thought bubble. Y square root of y divided by square root of 2. So 1 over square root of 2 then comes out, and then we're left with that. And when we do the integral, we get 1 over square root of 2 to our brackets, y increase half by 1, 3 over 2 over 3 over 2 between the limits 1 to 4. So this then becomes 1 over square root of 2, 2/3, 4 to the 3 over 2, minus, again, 1 over square root of 2, 2/3, multiplied by 1 to 3 over 2. So here we substituted the 4 into the equation, and here we substitute the 1 into the equation. So this would then be 1 over square root of 2, 2/3, multiplied by 8, minus 1 over square root of 2, 2/3, multiplied by 1. And this equals 14, 3 square root of 2, which is 3.3 units squared. We're asked to find the area bounded by the curve y equals x squared and y equals 3 minus 2x. So if we quickly draw this, y equals x squared is our parabola, which goes through 0, and y equals 3 minus 2x would be a negative line going through like this. So this is y equals 3 minus 2x, and the area that we're trying to find would be this. So first of all we need our points of intersection, which would be here, A and B, and we need to determine which would be f of x and g of x, because we're going to do the definite integral from b to a f of x minus g of x dx. So we have x squared. To find our points of intersection, x squared equals 3 minus 2x, x squared minus 3 plus 2x equals 0. So we factorize and we get x minus 1 and x plus 3. So our x values are x equals plus 1 and x equals minus 3. So our a is minus 3 and our b is 1. Now we need to either do a test strip or from our graph or our diagram find out which is the top line. So we can see that y equals 3 minus 2x is the top one, so that's f of x. So we have f of x minus g of x becomes 3 minus 2x minus x squared. So our definite integral area equals from minus 3 to 1, which is our limits, 3 minus 2x minus x squared dx. And when we do that, this then becomes 3x minus 2x squared over 2 minus a third x cubed, and the limits are minus 3 to 1. And then when we work that out, this becomes 5 over 3 plus 9, which equals 32 over 3 units squared. Okay, the area bound by two curves, y equals x squared and y equals, or let's make this x equals y squared. So if we draw a quick diagram, our y equals x squared would be our parabola going through 0 here. And our x equals y squared would be our parabola going through this point here. So we're interested in the area bounded by the curves, which would be this area here. So first of all we have to find our points of intersection, which would be A, and this one, which would be B. So we have x squared equals square root of x, because when we have x equals y squared, y equals square root of x. If we square both, we get x to the power 4 equals x. So x to the power 4 minus x equals 0, x cubed x minus 1 equals 0, so therefore x is either 0 or x is 1. So our point A is 0 and our B is 1. Now we need to determine which is our top, which is our f of x, because we're going to do f of x minus g of x between 0 and 1. So our b we said was 1 and our a was 0, and that's going to be dx. So we need to determine which is f of x. So if we choose, say, y as 0.5 and then put that into our strip and work out the top one. So y equals x squared for 0.5, that would be y equals 0.5 squared, and for this one it would be y equals square root of 0.5. This works out as 0.25 and this works out as 0.7. So the higher value is x equals y squared. So this is our f of x and this is our g of x. Okay, now we can do our definite integral. So the area is integral of 0 to 1, the top curve, which we said was square root of x minus x squared dx. And then when we do that, we didn't do the integral, it is x to 3 over 2 over 3 over 2 1 0 minus x to the power 3 over 3 to those limits. This works out as 2 thirds 1 minus 0 minus 1 third 1 minus 0, which is 2 thirds minus a third, and the answer is 1 third. Here we're going to have the area bounded by these two curves. If we draw a quick diagram, it's going to look y minus 2x is going to be a straight line, negative, so it's going to go like this, and our curve y minus 2 is going to be a curve which looks like this and then intersects here at the bottom. So something like that, and we're interested in this area here. So this is our y, this is our x. The points we're interested in are intersection points B and this intersection point A. So how will we do this? First of all, let's get everything in terms of x. So for y equals 2 minus x, we have x equals 2 minus y. For x equals y minus 2, we get x equals y squared minus 2y. So for our intersection points we have 2 minus y equals y squared minus 2y. So 0 equal, if we bring it all to one side, y squared minus y minus 2. Okay, and this is a quadratic, and when we solve that we get 0 equals y minus 2 y plus 1. So y equals plus 2, y equals minus 1. So our a equals minus 1 and our b equals plus 2. So now we can do our definite integral to find the area. So this becomes integral of minus 1 to 2, and our top line, if we don't know which one it is from our diagram, we can work it out by just doing a test line. So our top line is 2 minus y, which is this one. That's our f of x, 2 minus y, and we're going to subtract that from that g of x, which is our y squared minus 2y, and that's going to be dy. So when we get rid of the brackets, we get definite integral 2 minus 1, 2 minus y minus y squared plus 2y dy. When we tidy this up, this becomes integral of minus 1 to 2, so 2y minus y, we're just left with y minus y squared, and then just tidying up, we get minus y squared plus y, which is this one, 2y minus 2, no sorry no, 2y minus y, which leaves us with just a y, and then we're left with the plus 2, and that would be dy. And then when we're going to do the integral, we get this equals minus y cubed, we increase the power, divide by that, 3, plus y squared divided by 2 plus 2y, and we're going to do that between the limits minus 1 to 2. This, when we put the limits in, then becomes minus 8 over 3 plus 4 over 2 plus 4. That's using the 2, and then when we put the minus 1, this becomes 1/3 plus a half minus 2. And then we work that out, the answer is 27 over 6 units squared. I'm going to have a look at definite integrals involving trig functions. Trig functions. So if we have the definite integral between 0 and pi over 4 sine x plus cos x dx, this then becomes definite integral pi over 4, 0 to pi over 4, and then we can split these into two, so that would be sine x dx plus definite integral from pi over 4, 0 to pi over 4 of cos x dx. When we do this, we get minus when we integrate sin x we get minus cos x, and between the limits 0 to pi over 4, plus when we integrate cos x we get sin x, and that again is between the limits 0 to pi over 4. So this, when we do the substitution for pi over 4, becomes, let's just do it a little bit larger, minus cos pi over 4 minus cos 0 plus sine pi over 4 minus sine 0. Now sine pi over 4 is square root of 2 over 2, and cos pi over 4 is square root of 2 over 2. Cos of 0 is 1, minus a minus is plus, so just bearing that in mind we get this minus cos pi over 4 is square root of 2 over 2, then this minus minus becomes a plus, cos of 0 is 1, and then we have plus, again square root of 2 over 2, and then minus sine of 0 is 0. So this is nothing but minus square root of 2 plus square root of 2 cancel each other out, and we're left with 1 minus 0 equals 1. And that's our answer. Just as a matter of interest, let's have a look at the area under a sine curve. So we know that when we have the sine curve like this, it goes up to 1 and it goes up around like that, and we have 0 here and pi there, and we're interested in this area here. So this then becomes the definite integral of pi 0 to pi sine x dx. So when we do the integrals, integral of sine x is minus cos and we're going to do that between the limits of 0 to pi, and this then becomes minus cos pi plus cos 0. Why it should have been minus cos of 0, but we got the minus next to the minus, that becomes a plus, so it becomes plus cos 0. So this then is minus, and the cos of pi is minus 1, and this plus, and the cos of 0 is 1. So a minus is 1, 1 plus 1, 2. So the answer is 2. The best way to remember cos and sines is, like we discussed before, is the projection onto the y-axis. So if we had this minus cos of pi, pi is over here, this would be the cos projection, yeah, onto the x-axis, and this would be minus 1. Similarly, cos of 0 is the projection onto the x-axis over here, and that would be 1. When we're talking about sine, we talk about projections onto the y-axis, which would be over here. So if it was sine pi over 2, that equals 1. A very important technique used when we do definite integrals is that we can sometimes change the limits to make integration easier. So it's used when we have u substitution and definite integral. And we change the limits. So what do we mean by that? So if we have a definite integral, say between 4 and 9, those are the limits of x, square root of x plus 5 dx. So in the normal way, if we were doing integration, we have u substitution, or we need to use u substitution, so we use u equals x squared plus 5. Our du then becomes 2x dx, and our dx is nothing but du over 2, or half du. So when we replace this by our u's, using u substitution, we bring this half out of the integral, integrate between the limits 4 and 9, u to the half du. So this then becomes, bring half back, when we do the integration, half plus 1 goes to 3 over 2, divide by that, 3 over 2, between the limits 4 to 9. This then becomes 1/3 u to the 3 over 2, limits 4 to 9. And then when we put the 9 in, oh sorry, we have to replace the u in this one in the u substitution. So we have 1/3 x squared plus 5, because our u was x squared plus 5, to the 3 over 2, limits 4 to 9. So then when we put our limits in, this becomes 1/3, x is now 9 squared plus 5 to the 3 over 2, minus, then when we put the 4 in, this becomes 1/3, 4 squared plus 5 to the 3 over 2, and when we work that out, this becomes 1/3 of 86 to the 3 over 2, minus 1/3, 21 to the 3 over 2. Now let's have a look at the technique of changing the limits. So we have the u that we got here, u equals x plus 5, and we just put the lower limit in first, so this becomes 4 squared plus 5, which is 21, and then put the upper limit in, 9 squared plus 5, which is 86, and then just in the normal way we have u to the half du. That brings us down here to our integral of 1/3 u, so we're keeping the u, 3 over 2, this was to 86/21, and now we can just put our limits in, so this becomes 1/3 of 86 to the 3 over 2 minus 1/3, 21 to the 3 over 2, and that are the same. So it's much easier to do. Okay, let's have a look at definite integration of parametric equations. First of all, we just follow these rules. Number 1, we express x and y in terms of the parameter. Then number 2, we change the variable. And then number 3, we insert the limits of the parameter and do our integration. So if we have a curve and the equations, the parametric equations are x equals at squared and y equals at, and we are asked to find the area bounded by the curve at t equals 1 and t equals 2. So the area is definitely integral b to a of y dx, and y equals 2at. So this then becomes area equals definite integral b a to b. Our y was 2at. So this should be 2at. And well, this then is dx. So when we replace our dx, so x equals at squared, and our dx over dt will then become 2at. Our dx is 2at dt. So using that, we can then sort of insert the limits after and change the variables. So the limits then become, so the area equals the limits 1 to 2, 2at, and then here we had 2at dt. So when we work this out, this then becomes the integral in 1 to 2, 4 a squared t squared dt. Which then is, when we do the integration, 4a squared, because a squared is a constant, t3 over 3 limits of 2 to 1. And this equals 4a squared 8 over 3 when we put the limits in, minus 1 over 3, which is 28a squared over 3. Okay, in this parametric equation we have x equals a sine theta and y equals b cos theta, and we want the area under curve where theta equals 0 and theta equals pi. So the area, as we said before, write it out, is definite integral a to b y dx, which is integral of a to b and y here is b cos theta dx. Now we want to work out what dx is. So dx in this case would be a, and then sine theta becomes cos theta, so that's a cos theta d theta. So this then becomes definite integral between the limits 0 to pi. So this was b cos theta dx, so this is b cos theta, and dx was a cos theta d theta. And now we're ready to do our integration, so let's tidy this up. So this is the integral between 0 to pi, and then our a and b come together, ab cos squared theta d theta. Now this ab is a constant, so it can come outside, and we just need to integrate cos squared theta. So our cos squared theta integration, we use our half angle, cos half angle rule. So if we do a little thought bubble here, so cos x over 2 equals plus or minus square root of 1 plus cos x over 2. So this then means that cos x is equal to square root of cos 2x, because it was half x becomes an x, cos x then becomes 2x over 2. So the integral of cos squared x dx then becomes the integral of all of this, cos 2x over 2 all squared, which is get rid of the square root, becomes 1 plus cos 2x all over 2 dx. So this then, if we take our ab outside the integral, then becomes the integral of, now let's carry on with this integration. So this, then we can take the half outside, the integral of 1 plus cos 2x, which equals a half x plus a quarter sine 2x plus c. So coming back here, if we apply this, this becomes theta over 2, which is the half x, plus sine 2 theta over 4 from the limits 0 to pi. This equals ab pi over 2 and this is pi ab over 2. That's the answer. Applications of integration, and particular volumes of revolution. If we look at our previous integration that we did for area, we have the x, y, and a curve f of x, and our limits a and b, and 0 there. So for volumes of revolution, this plane figure that we had with our definite integration is bounded by f of x, the x-axis, and the ordinates a and b. If we rotate this plane figure around the x-axis by one revolution, we generate a solid symmetrical about 0 and x, so along the x-axis. So basically what we would get is, if I just do a little model here, and I've split this into slices, the solid, so we can see. So this is our top, this is our curve going up, and we split this into slices, this being our A, the first disc, and this being our B, the second disc, the last disc. And in between we have the thickness of the discs, which are delta x. So when we look at it in that way, we can see, like, when there's a solid figure generated which looks like a cone. So this is our disc on the top, and it's coming down something like this, and this is our thing on the bottom, and this is all solid. Okay, so that's what we're looking at there. So a solid figure generated. This is the screwdriver, represents our x-axis. These strips, when rotated, form a solid of revolution, which looks like that. So what we can think of this as is, again, let's draw a little x and y axis. So we have x, y, this is our f of x going up, and if we have take a little strip here, this would be the thickness of the strip would be delta x, or dx. This we would have a point P, this we would have a point Q on the strip. Delta x is the width of the strip at x, would be from 0 to here to where delta x begins, and our y would be from this point here where P touches the curve down here, that would be y. So this over here is y. So what happens when we rotate this strip around the x-axis? We get a volume generated. dV would be equal to approximately, just put approximately, not equal to, pi y squared dx. And if we took a lot of these strips together, the volume would be the sum of all those strips, which would be from x is equal to a to x equals b pi y squared dx. The errors in this approximation, it would be due to the step formation. But if we get this delta x tending to 0, the errors disappear. So as delta x becomes smaller and smaller, say we make the spaces smaller, or the thicknesses infinitely small, and push everything together, we can get a very good estimate of the area. And then when delta x tends to 0, then we get a total volume, the volume of the solid from A to B becomes pi y squared dx. Revolution. Find the volume generated when the plane figure bounded by y equals 5 cos 2x on the x-axis and ordinates 0 and pi over 4 rotates about the x-axis by 1 revolution. So we know that v equals pi, and our integral is from 0 to pi over 4 y squared dx. From this we get 25 pi, because we're multiplying 5, we're squaring the 5, integral from 0 to pi over 4 cos squared 2x dx. Now we need to use our double angle formulas. For cos squared x we use, let's have a look, put a little thought bubble here. So cos 2 theta equals 2 cos squared theta minus 1. So therefore cos squared theta, which is what we want there, equals a half 1 plus cos 2 theta. Okay, so we're going to use this and substitute into there. So that becomes, move up a little bit, 25 pi over 2, definite integral between 0 and pi over 4, 1 plus cos, now that was 2 theta, so we want 4x instead of 2x, and that'll be dx. Now when we do our integration, we get 25 pi over 2. So we integrate 1, we get x plus sine 4x all over 4, and our limits 0 to pi over 4. Now we substitute our limits into our integral or our integrand, and we get 25 pi over 2 pi over 4 plus 0 minus 0 plus 0, and that equals 25 pi squared over 8.